So welcome to Intel. This is kind of a teaser presentation, not a full-blown meal here. So we live in exciting times. Compute has evolved greatly over the years. There's great products out on the market today. But one of our goals is to continue to deliver great products and even better products going forward. And we are at a crossroads here where we are moving beyond conventional computing and into the space that this conference represents. So let me first talk about who we are as a research organization. Starting on the left-hand side of the page, we have an organization that works on physical technology. Their number one job is to keep Moore's Law going, and they've been at it for a long time, and we expect that they will continue. They also do novel integration, so putting different pieces together in a physical way, different than simply building a larger and larger die with lots of functions. On the right-hand side is the group that is essentially my day job. Intel Labs is focused on what does the future product look like. So it might be a feature, it might be a piece of an overall product. But the more exciting part of the job is trying to predict the future and say, where will Intel be in 5 years, 10 years, and 15 years' time? And across the bottom is the third leg of the stool, university research. We do this because we can't, of course, invent everything ourselves. We will have blind spots. We want to engage as large of a community as we can, both from a standpoint of pushing the frontier, as well as these are our future collaborators, whether we hire them and they come work directly for us, or whether we will continue to work with them as PIs for future projects going forward. So with that as a setup, my favorite quote from Arthur C. Clarke is the one at the top of the page. And I truly believe that we're at a time where we can implement a lot of the things that people have dreamed about in the past. Starting on the left, our logic technologies can put a few billion transistors in a square centimeter. Not to be outdone, the storage class memory people can put 100 to 200 billion logical bits in a square centimeter. Our industry ships on the order of about a sextillion transistors every year. 99.99 of those are storage. I suspect that a lot of them are storing cat videos, but nevertheless, we're shipping a tremendous amount of capability for storing data and analyzing data. And the beauty of Moore's Law is getting better every generation, and those generations multiply exponentially. So there's lots of talk about Moore's Law being dead. I know it's a subject that comes up. The first year I heard that was actually my second year at Intel, 1985. We go through this periodically every few years where someone says, oh, well, this can't possibly go on. One of the latest ones is, oh, well, Dennard scaling has ended. Well, sorry, Dennard scaling kind of ended 15 years ago and no one really noticed, and so I think we can keep going for a while further. We can see comfortably ahead to the 5 nanometer node. Now that's our naming, not necessarily other people's naming. But to be fair, Moore's Law is evolving. It's not the same Moore's Law as when I started at Intel. It's not the same Moore's Law of 10 years ago. And if I had the time, I could go through the details across this progression and say how Moore's Law has changed over time. But I want to leave with a couple of points that help inform the compute discussion that I'm going to go into next. First, while we can continue to scale logic, are there certain things that are easier and certain things that are harder? So more transistors automatically allow you to do more parallelism. So building a part that runs more threads in parallel is sort of an easy thing to do. Running at a higher frequency can be done as well, but it becomes limited by essentially the access to external memory. And if I look at DRAM scaling, for instance, the latency scaling has slowed way down. So it becomes harder and harder to make a faster compute because the memory hasn't gotten faster. The memory people, on the other hand, can make things more parallel. And so there are ways to go forward with compute to drive more parallel workloads. That's important because the neuromorphic stuff that we're talking about today is one of those parallel workloads. So the question is not, can we keep going with technology, but really, what can we build with the technology that we see on the horizon and the technology that we'll be working on after that? So any prediction of the future starts with, what is your view? And I will say that I have multiple views of the future because I think multiple things will happen in parallel. One is the future that people like to talk about, which is better devices. And in this context, I define a device as something that the primary purpose is to interact with a human being. So you can think of your phone as a device, a PC as a device. Many of the things that you will interact now and in the future, your smart refrigerator, for example, from that point of view will be a device. For that particular future, if it's something that you carry around, then people want more convenience. They want longer battery life. They want it to be able to connect seamlessly. And we can deliver all of that. What is a little bit harder is delivering natural interfaces. It's a little bit harder for you to pick up a new device you've never seen before and instantly figure out how to interact with that. That's a different kind of compute that we are working on and we want to enable going forward. The second thing is electronics essentially disappear into the infrastructure, whether that is a smart road sign or the telecommunications that happens behind the scene, or the things that run the air conditioning and the heating in the buildings. That ambient computing, again, requires a different kind of compute. And it is, again, something that we're working on today. Now, we don't get as much credit for that because people forget that it exists. But when it stops working, when your traffic lights stop working and they don't synchronize, you notice the failure more than you notice the success. And then, of course, the third future is Skynet, the cloud, the all-seeing, all-knowing thing in the sky. And we're working on that one as well. So we organize ourselves from a program structure into these 7 different buckets. 2 of them on the outside corners belong to the components research organization, the Moore's Law, the novel integration. The bottom is really the pillars, the foundation of the technology. So in the foundation, we have security and we have sense-making. Security is one of those things you can't design in after you're done. And so you have to begin working on that early and thinking about it from a negative point of view as well as thinking about it from a capability point of view. A simple example, if we work on quantum computing, then we also have to work on post-quantum cryptography because it's not okay to deliver one solution that breaks something else. The other pillar is sense-making. And the reason sense-making is there is because increasingly compute is used to understand the real world, not the world of banking or the modeling or things like that. And that is a really different kind of problem than we've had to face in the past. The core of our business is compute, and the second half of my talk is compute, but I'm going to start with setting up the problem of what do we want compute to do going forward. So this is a communication example. Think of the densely crowded stadium on the left or the densely crowded traffic on the right. Those are examples where density, interference, the ability to connect is an important part of that. In addition to that, networks today are increasingly mobile. So having an element of positioning is an important part of that. In fact, we're going to need an element of positioning as we do beamforming and directional antennas. It's not simply to keep track of where people are at. Depending on the application, the connection needs to be highly reliable. So if you're using it to communicate to the car in front of you that you're speeding up and you're going to follow them closely, well, you want that link to be very reliable. It has to be environmentally context aware. If you're downloading a video and a more higher priority traffic needs to come through, well, then this system needs to adjust to that. And this drives the need for distributed intelligence. So we're going to put more and more compute into the network, into the infrastructure itself. And that needs to be cooperative. It can't be, I'm going to take all the bandwidth for myself. That will drive different systems, the autonomous systems that may be in your cars, the systems that will be in your factories, or even the systems that will be in your home. All of those things require more compute for the communications aspect than we've had historically. Digging a step further into autonomous driving, we have the problem of you have a model running on the car interpreting the environment. That's the sense-making part. The model needs to be periodically updated with new information. Typically, that's going to happen in the cloud. There needs to be security around how do you transmit the information, what amount of information is exposed. It gets to be a really complicated problem when you get behind the surface and dig into the details. For sensing, we're currently about in the middle of the page. So we already know how to capture the data. We already know how to do the first level inference on the data. We can capture the context by having multi-channel things. Making sense of the data is the harder problem. So we can discover correlations empirically. We can put the data in the context because we've captured some of the data along the way. And we can generate a hypothesis. What we are unable to do yet, that we're working on, is to really do a level of personal adaptation. So discovering routines of a person. On my phone, it'll say, oh, you need to leave for work now, and I've never said where work is. And then during a week where I'm in multiple buildings, it gets very confused. So discovering the routines and being able to adapt is something that it struggles with. Making recommendations, depending on the context, is something that it struggles with. And then finally, the continuous learning. I'm really looking forward to the day that my smart device is actually smart and not forcing me to be smarter to figure out how to make the most use of it. We have run some experiments around adaptive learning, and it's showing interesting results. It's not a done thing, but we find that this is a classroom setting. We have computers in front of the students, so it captures a video of them working. It is a computer, so it can capture the context of what they're working on. We have the teacher observations, and we put all those together and we build a model. What we find is when we put together a single channel of information, we get to a certain level of accuracy. I'll simplify and say, let's say 60% accuracy at predicting whether the student is engaged, whether they're bored, whether they're frustrated, whether they're just not paying attention at all. If we combine multiple channels of information, let's say the visual appearance along with how they're moving the mouse and how they're typing, we could get to a higher level of accuracy, let's say 70%. But if we make the model adapt to the person, we can get still higher accuracy. And so this is a proof point of suggesting that the future of AI is not about collecting data around everybody, but really personalizing and adapting to you. So with that said, what does that mean for compute? So compute right now is largely around moving, it's like doing banking or doing simulations or a lot of things other than the things that I've just talked about. Now those workloads, the things that are machine learning and AI and things related to that are the most rapidly growing segment within the field. So we need to pay attention to what does it take to make those go. So today, machine learning is really empirically driven. With enough data, you can make sense of it. It can cope with, in many cases, complicated and varied data. And in some narrow problems, it can achieve human accuracy. But step outside of that region and humans do better. Humans are more adaptable. What we want to get closer to, and we won't be there for a while, is get to the right-hand side of the page, something that looks more like natural intelligence, something that can handle ambiguity, that can reason about context, and that can be autonomously learning as opposed to being fed lots of data. I've read people saying basically, if you have 10,000 examples of something, you should use deep learning. Well, what if you don't have 10,000 examples? What if you want to do something with a lot less data? So, can we be inspired by biology? Now, I cringe to show this to this crowd because all of you know a lot more about this than I do. But simplifying, in your nervous system, you have specialized data capture at the edges. You have generalized feature extraction in the middle. And then you have hierarchical representations that you can reason about into your central nervous system. We tend to talk about it as a feed-forward network, but in fact, the real biology has an equal amount of bidirectional feedback. What you perceive is influenced by what you're thinking about. What you think about influences what you think, and so forth. So today's systems tend to only look at a tiny piece of the complexity that's there in natural intelligence. So we kind of know how to do compressive sensing. We kind of know how to do deep learning. But I think we've only scratched the surface of where we want to go from a standpoint of being smart and cognitive. We can wrap structure around things, but we really struggle to do meaning. So now let me talk a little bit about some possible solutions. These are not a complete set. They are not all that they're working on, but they tie together some of the things that I've talked about earlier, where the ability to operate on data is different, the ability to run in parallel is different. So you may be surprised at the first thing, which is an FPGA. It's like, well, who cares about that? FPGAs have been around forever. Well, yes and no. FPGAs are now larger and more flexible than they've been before. An FPGA at a smaller scale is simply a spatial array of configurable elements. Does that sound similar to what we might have in our nervous system? Well, yes. It's also a chance to be a little bit humble, that we can't predict all the algorithms that we're going to use in the future. And so having programmable hardware that can adapt to the algorithms that are coming is an important part of that. Microsoft, for example, in their Brainwave initiative have chosen FPGAs as an example of hardware to go for those future algorithms. Secondly, as you'll hear later today, we're working on neuromorphic computing. We initially started this project thinking this would tackle the compressive sensing in a more energy efficient manner. Since we've come to believe that there is a lot more to it, a lot more opportunity there. I'm not going to delve into the details. Whatever we choose to do as a technology, there's always something more radical. And so my placeholder here is quantum computing. And I think it is amusing in some sense that the deep learning people are hoping that quantum computing helps them solve the weight optimization problem. And the quantum computing people are hoping that the neural people can figure out smart decoders that allow them to do quantum error correction. Again, this is an example of a novel architecture that we're working on that we think will have opportunities as we go forward. But I want to take a moment and step back from the hardware and talk about the problem of what runs on the hardware. And that requires us to think differently than we've done in the past. Conventional computing really is about writing a known procedure and then generating an answer. So we tend to focus on the hardware here at Intel, but in fact, a lot more dollars, a lot more time is spent debugging the software stack, making the software stack do things that we hadn't anticipated when we began building the hardware. So that equivalent to what does the procedure look like, as you go into deep learning, it's really about preparing the data. You have a known set of answers, in this case, the supervised machine learning. You start with labeled categories, and you're using software to generate a procedure from that, which you then use to do inference in the future. So just like we tend to focus on the hardware, we may focus on what that model looks like, when in fact focusing on the data is the more important thing to do. For neuromorphic computing, particularly in the messy, recurrent manner that I've shown here, remember at the local level, a lot of the wiring is random. It's really about having many concurrent procedures that are all running at the same time. And the reinforcement learning is really about separating out the procedures that work from the ones that don't. That's a very different equivalent to programming, and it's something that we need to spend more time working on, not just focusing on what the hardware does. And to be complete, quantum computing, you start with a series of possible answers, you superimpose them, and then you do operations, and you raise the probability until you get the answer that you want. It's almost magic. It's like dumping answers in a box, and from the rotation and the shaking of the box, you magically get your answer to be at the top when you reach in. Again, we're going to have to spend more time on quantum algorithms and how to make that work. Now, I often get asked, particularly around quantum, doesn't quantum make everything else obsolete? And of course, the answer is no. All of these things are going to be good at certain things and not very good at others. Further, a general purpose machine can, in fact, simulate the others as well. And so all of these are going to coexist going forward, even as we make progress and we open up new opportunities for problems. But that's not our most exotic project. This is what I would consider our most exotic project. So we're partnering with Princeton. We're doing functional NMR on people as they think about things. It's interesting to Intel because it's a very hard computational problem. You collect a lot of data. You have to make sense of it in quasi-real time. And so we learn a lot for how to schedule compute, how to map compute to our systems, how to make compute better. But the goal of the science is to better figure out how your brain works. And so the opportunity here, if it succeeds, is basically to have more information that allows us to design still better computer systems going forward. So 3 takeaways. First, as I said, we live in magical times. We can implement things that people have only dreamed about before. And the exciting part is working across disciplines, working at the boundaries between 2 things. So in this case, microelectronics and neuroscience, many of those things are very interesting because they're not well studied, because they're not well understood. And we'd like to join you as part of our overall collaboration in creating the future. So with that, I will remind you, you are here. Thank you. We build a lot of low-power things. We've built chips that basically are essentially self-sustaining with a 1 centimeter solar cell. They operate at microwatts. What we are trying to determine is where the market is going for that. If we have technology to build, let's say, the smart dust that you scatter in the environment, who pays for that? What do you do with it? How about the communication problem? What our customers ask for drives what we deliver in the near term. What is possible drives what we can deliver in the longer run.
Well, how about cell phone chips?
Oh, we can certainly make lower-powered cell phone chips today. We can make longer battery life. Our customers are not asking for that. So,
I have a question.
Yes.
So I recently heard that some companies, perhaps including them, is changing architecture for different real-life data, so kind of working on different architectures. Are you working on modifiable architectures so that you'll not have to, for every data, kind of
Without giving the roadmap, I'll say yes, we are working on that. I can't give any particular details around that, other than the FPGA example. So, all right, I'll let you get to your panel.